The first of the Gauss-Markov assumptions focuses on homoskedasticity. And homoskedasticity, that's the technical term for it. And what I want to do is just scroll up and show you what I said here is that the residual variance, error variance, is constant across predictors. So what that means is that for every value that you predict of y, that the deviation between that predicted value and the observed value is going to be consistent for all values or all sets of values across your prediction range. And the best way to capture that is to work backwards and first focus on what the equation of the line is in multiple regression. So we've learned that y equals bx plus a plus error. And error is that residual, right? That part that we're not predicting. To simplify this, what I want to do is just change bx plus a into y hat. So the equation is y equals y hat plus error or residual. And why is that? Well, remember that y hat is essentially the predicted value of y given this line of best fit of bx plus a. Now this is obviously a bivariate regression. So what we can do is take the bx plus a and replace it with y hat, leaving y equals y hat plus e. And if we move things around, simple substitution, we have e, the residual or error, equals y minus y hat. So the reason why I want to re-emphasize this is that our residual is the deviation between the observed. So I'm just going to put this here. So residuals, E, are equal to what is observed minus what is expected. Now what do we expect from these residuals with this assumption? Well, we expect the same amount of variability across the entire range of our prediction. So what that means is we want to make sure that all predictors produce expected values and deviations from between expected and observed that are consistently variable across a range. So what I want to do is I'm going to, just to demonstrate a violation of this, what I'm going to do first, actually, let me do this, y yep, tilde dat 3. And I'm just going to show you what this looks like. Whoops. If I don't make typing mistakes, this is easily plotted. So take a look at this. What we have here is we have x and we have y. And look what happens. They're all tightly bunched here, but then as we go up, there are all sorts of spread. So it's a fan-like spread. And that fan-like spread is going to come out when we look at our regression diagnostics. So you can see here our residuals versus our fitted values. Look at what happens to this spread. The residuals, remember residuals are just observed minus expected y's, and that these residuals become more variable as we go up our fitted value range. Okay, so now why is that important? Well, that's important because that says that our ability to predict y is really dependent upon the values that we have of x, and that the higher values of x produce less dependable or less useful values of y because there's a lot of error or slop around those expected values. Now, how does this come about? Well, it comes about from multiple things. And first, the homoskedasticity assumption. The opposite of that is heteroskedasticity, which is what we're observing here. So how does this come about? It comes about potentially from measurement error. Sometimes our instruments are really sensitive within a particular range, but insensitive outside that range. It can also come from unmeasured or unspecified moderators, where you have, obviously there's variance here at the outside that is not accounted for in our prediction model. So if we don't account for that variance, that variability turns into be a detriment and a violation of one of the assumptions in regression. So this first Gauss-Markov assumption has to do with the spread of the residuals. If we have an increasing or decreasing spread of the residuals across all of our expected values or all of our predicted values, that what we're going to have is we're going to have a poor prediction model. So assumption one, homoskedasticity. The next video will deal with our the distribution of those residuals, so stay tuned for that.